Hi, I'm Fernando Pereira, and I shall be presenting to you the paper Impact of Obfuscators and Code Optimizers on the Accuracy of Program Predictors. This is a work that I did with 5 other colleagues. In particular, it's the main topic of the master dissertation of Thais Damasio, who is the first author of the paper. The paper evaluates different techniques to solve algorithm classification. This is the problem of, given a set of programs, finding two that implement the same algorithm. In other words, we want to find programs that solve the same problem. As an example, here we would like to say that this program is adding numbers and not computing their maximum or computing factorial or sorting them and such. Notice that these programs that we need to match up will have different codes. This problem is often called clone detection too. Clone detection is very important, for instance, to identify malware or to identify software plagiarism. Usually, these homework grading systems implement some form of clone detection. And given that the problem is so important, there has been much effort to evade classification. Basically, an evader is a tool that transforms a program to hide its true purpose. Obfuscation is a typical example of an evader. But then, optimizations are evaders too. The optimizer might change a program as much as an obfuscator. Clone detection, in general, will be undecidable. We are talking about solving program equivalence, so typically classifiers are stochastic, and there is a kind of arms race between evaders and classifiers. And many, really many results have been produced in recent years. For instance, there are many ways to convert a program to a vector of numbers to classify it. So, is there a representation that's more effective? Or how effective are code obfuscations to evade prediction? And mind it that there are many obfuscation techniques. And can optimizations revert obfuscations? Some obfuscation techniques are very naive. Other robust obfuscation techniques. In total, our paper explores 8 such research questions. And to answer them, we have produced a game-based framework which pits classifiers against evaders. We have 4 games in total. They differ on which resources are available to the classifier and to the evader, but notice that the classifier and the evader can be any tool. Game 0 is the easiest to understand. Classifiers and evaders have access to the same dataset of programs. Part of this dataset will be used to train the classifier. The other part will be used by the evader to challenge the classifier. The evader does not perform any obfuscation. In game 1, the evader will have access to an obfuscator. Thus, it's allowed to transform a program before challenging the classifier. Game 2 is like game 1, except that the classifier knows which obfuscator the evader uses. The classifier can use this obfuscator during training. In game 3, the evader can obfuscate programs. The classifier can optimize the programs though. So the evader obfuscates a program to challenge the classifier. And then the classifier can apply an optimizer on this challenge. This hypothesis here is that optimizations can revert obfuscation. So, we have organized all the machinery to carry out these games into a framework, which we call Yali. Yali is publicly available as an artifact. Indeed, our paper is pretty much a tool paper. We have this tool, Yali, which has been evaluated as an artifact, and which people can use to see which classification and obfuscation techniques are more effective. The framework provides basically 3 things: different classifiers, different evaders, and a dataset. In total, we have 9 classifiers. These are essentially LLVM passes that take a program and convert the program to a vector of numbers for classification. We provide a number of stochastic models that we took from previous work too. We did not implement any of those things. We took everything from previous work. We also provide evaders. We have adapted OLVM to work within our framework, so there are different obfuscation techniques. We also can use optimizations as code obfuscation. And we took 4 different code obfuscation techniques from a repository by Weiwei Zhang. And as a dataset, we use Podge 104. That's a suite of 104 programming problems, each with 500 solutions. And we have also curated 48 different versions of the Mirai malware. And then, with this framework, we can explore many different questions. I will show a few. First, which program representation would be the most effective out of those 9 that we had? For a simple comparison, we have used them with a neural network, which was published in 2018, exactly to classify programs. In fact, we have 2 versions of this network, one that receives graphs and another that receives simple vectors. And then we can measure the accuracy of each classifier. In this case, how often the classifier finds the right problem that a program solves. The expected accuracy of a random classifier would be less than 1%. But as you see, we get much more. So definitely these classifiers, they are not random. But something that was surprising to us is how well a classifier based on histograms of opcodes does. It was the second best classifier that we had. But mind that histograms are very simple. If I take a program like this, a histogram is just a table that counts how many times each instruction appears in the IR of the program. This is the histogram for LLVM. It contains 63 entries, 1 for each opcode. For instance, the third index represents branches, and we have 6 branches in the program. Anyway, we are surprised. The other representations are much more complicated, and yet histograms were doing pretty well. Let me show you results for another research question. We want to compare different models to see which one better use the embeddings that we have. That's what we call Game Zero. Classifiers and evaders use the same program without transformation, and we have 5 different learning models. These are typical stochastic classification models. And again, we are reporting accuracy. In this example, I shall use the histograms and the program representation. The histograms as the program representation. We got something between 40 and 80% of accuracy with different models. That's much more than 1% of random classification. Random forests work consistently better across our different games though. Now let's see how code obfuscation impairs classification. We shall be using the same 5 models as before, and again reporting accuracy. But this time, the evader is allowed to change a program before challenging the classifier. We shall compare different transformations. On the top, we have LLVM, which is an obfuscator built on top of LLVM. It uses 3 different transformations. We use also Clang -03 as an obfuscator. And we took 2 obfuscation techniques from previous work. They are described in this paper by Weiwei Zhang and his colleagues. The next figures will superimpose the accuracy of the classifier with and without obfuscation. So as you can see, obfuscation usually reduces the accuracy of classification. In some cases, it makes classification just like random guessing. Something interesting is that one of the obfuscation techniques that we used had no effect on the LLVM representation. The SSA conversion that LLVM uses was reverting most of the effects of naive obfuscation based on renaming variables and adding constants to the code. Now, what happens if we give the classifier knowledge of the obfuscator? The classifier could use it during training. In this case, classification becomes much better. It's almost like in Game Zero. Although OLVM is still resistant to an obfuscation-aware classifier. And a final question here. Can optimizations revert obfuscation? That's what we call Game 3. Not if the obfuscator is OLVM. In this case, optimizations are not really good at reverting the transformations. But if we use the other obfuscators that we had, like those from previous work, then the optimizer totally reverts the transformations. We call these obfuscation techniques naive. So let's see a few things that we learned from this research. First, histograms are pretty effective. They are even better than fancy embeddings described in recent literature. Actually, we liked this result so much that our original title was jesting a bit with it. But then the CGO reviewers asked us to back down, and we acknowledged that we didn't really have enough data to support our findings. Second, sometimes you can use the optimizer as a code normalizer to revert the effect of obfuscation. But there are some pretty robust obfuscation techniques. For instance, control flow flattening is very resistant against optimizations. But then, control flow flattening is not very effective against histograms. And there are also frail obfuscation techniques which optimizations revert, totally. And knowing the obfuscator really helps in classification. However, guessing the obfuscation is a hard problem. We explored this question in the paper. And that's it. Thank you for your attention. Feel free to ask any question that you may have. And if you are interested in this work, you can try our artifact.